So now we've got a general scheme for computing max flows and min cuts and a proof that they're equivalent. And next what we need to do is look at an analysis of the costs of computing things to try to figure out specific efficient ways to compute augmenting paths. So we already saw how to compute a min cut, so we'll just worry about doing the max flow. Find an augmenting path. Well, there's lots of ways to find an augmenting path. Any graph search is going to work. So let's just start with BFS, for example. If forward focusing terminates, that means there's no augmenting path. Does it always compute a max flow? Yes, we showed that. That's if it terminates. Does it always terminate? Does it oscillate back and forth? Well, it's a little more work to show that it does always terminate. If you have to, a few other conditions, for simplicity, we assume that edge capacities are integers, or there's other things that can be done with a choice of augmenting paths, and maybe we'll come back to that. But to figure out how many augmenting paths there are, that's the key that requires some clever analysis. And there's been a lot of different schemes studied to try to understand a way to first find the paths cheaply, and then decide to try to see how we can limit the number of augmentations. Let's look at an important special case, and it's true in lots of applications, where the edge capacities are integers between 1 and some big maximum u. A lot of the things that we talk about work when edge capacities are real numbers, but let's just talk about this case. One thing to notice in that case is that our forward focusing method always keeps an integer valued flow. We never take half a flow unit and put it through an edge. So it's always integer valued, because the flow in each edge is an integer, capacities are integers, and so everything stays to be an integer. Every augmentation either increases or decreases by the bottleneck capacity, which is always an integer. One thing that's definitely true is you only augment if you're going to increase the flow. You have to augment. You wouldn't augment if you couldn't augment by at most 1. It's definitely true that the number of augmentations is less than or equal to the value of the flow. There's what's called the integrality theorem that is important for some applications, and we'll come back to it, that says that there exists an integer valued max flow, and forward focusing finds it. It's hand-waving a little bit to talk about that, but we'll work with integers, and we'll be confident that we get to the answer. And so the proof of the integrality theorem is that it terminates, and the max flow that it finds is integer valued, and that's enough. But just to get an idea for what goes on, let's look at this bad case. Even when the edge capacities are integers, you could have a lot of augmenting paths, and we want to avoid this case. So look at this network here where we have S and T, and we've got 2 big capacity edges coming out of S, and 2 big capacity edges coming into T, and then we just have a little edge of capacity 1 going between those 2 intermediate vertices. Here's what could happen. So in the first iteration, we could decide that we want to push flow along the path that goes across the middle. Now we're going to look at a lot of different schemes for finding augmenting paths. So maybe a scheme says if we have a choice, let's take as long a path as we can find. So in this case, that's what it would do. There's another augmenting path that just goes from S to the left vertex down to P, but the algorithm, say it chooses this one. So we have an algorithm that chooses this one. So that increases the flow by 1. But then the problem is maybe the next time we make that middle edge a backwards edge, And so now we go through and increase the flow by 1 along that edge, and now we have a total flow of 2. And then maybe we alternate between these 2 schemes. Increment by 1 on the left, increment by 1 on the right. And it's going to take 200 iterations to finally get to the max flow. Whereas a different algorithm might have gotten it done in 2 iterations. And 100's not so bad, but maybe these weights are 1 billion or something. It would take 1 billion iterations. So that's bad news. That's too slow an algorithm. We want to try to avoid that. Now, there's an easy way to avoid that, and that's use the shortest path, or another way is to use the fattest path, the one that you can push the most flow through. That's just an example of the kind of pitfall that you want to avoid in trying to come up with an algorithm for choosing augmenting paths in Ford-Fulkerson. Now, the performance of the Ford-Fulkerson algorithm is going to depend on the method used to choose the augmenting paths. Here's listed 4 easy ways to pick augmenting paths, and they're pretty easy to implement. They're very similar to Dijkstra's algorithm and Prim's algorithm and others that we've looked at, but they lead to a different number of augmenting paths depending on the network. So for example, you could decide, let's use the shortest path. So that's just the augmenting path with the fewest number of edges. And that's just breadth first search, essentially, in the graph that ignores the full forward and empty backward edges. Now, it's been proven that there's no network for which the algorithm uses more than 1/2 E times V paths. So at least that's an upper bound that shows that it doesn't have this bad performance involving the capacity. I want to emphasize that this is a very conservative upper bound on the number of paths used. In an actual network, might not use anywhere near that number of augmentations. Another example is the fattest path. So that's the augmenting path with maximum bottleneck capacity. And again, that one is pretty easy to implement, very similar to our implementations of Dijkstra and Prim's algorithm, and we'll see in a minute. And again, the conservative upper bound on the number of paths taken by that algorithm is number of edges times the log of product of edges and capacity. But again, that's a very conservative upper bound, and in the real world, might only take a few augmentations to compute a max flow using that method. Or you could use a random path, which again is easy to implement, randomized graph search, or depth first search. Now, these conservative upper bounds are useful, but in real world networks, these algorithms are going to have running times that depend really a lot on properties of the network. So people use different algorithms in different situations. And the fact is that often we can get max flow problems solved even on huge networks with a relatively small number of augmenting paths.